Please try to understand it. Listen. So IB depends on WB dash, not on WB is telling. Okay. So up to here, please note down clearly. And last one more is here. What is WB W dash? Last term is WB W dash, which is being telling about your depletion region width. It is telling about the depletion region width on the base side. Depletion region width on base side. So these are the simple clear points for you according to the early scientist. So finally what I understood is WB is a physical width is divided into two parts in BJT. One with current will depend, one with current will not depend, because in depletion region current cannot flow, but in WB dash current can flow. So this is the story. Now what I want to explain in the class is simple logic. As your VCE increases, reverse bias voltage increases. VCE is nothing but collector to emitter voltage, which is a reverse bias voltage. If it increases, what the person is telling is your W dash, that is called depletion region width, will increase on the base side. That only we are talking the class. As the reverse bias voltage increases, the width of the depletion region also will increase. That means this width is going to penetrate this side as the voltage you are increasing. So in the lab, definitely you change the voltage characteristics. Output characteristics means VCE have to increase from 0 to VCC have to increase. As the VCE is going to increase, you are applying more and more reverse bias. Therefore, the immobile ions will spread more and more in the width of the base. As the W dash is spreading more and more, as this is spreading more and more, I have seen that the operating width is decreasing in the class. Your operating width is depending on your penetration. Therefore, your WB dash is decreasing in the concept. So WB dash will decrease. As WB dash decreases, but WB is telling, physical width is telling, I'll be constant. So I think inside widths are changing now according to your reverse bias mechanism. As the width of the depletion region is increasing, the width of the operation is decreasing, width of the operating point, correct? So as the width decreases, your operating width is decreasing, but the physical width, whatever you created, the material, that is not changing. So therefore, from here to here, the width is not changing, inside widths are changing. That is the basic knowledge he kept in the subject. So as VC increases, W dash will increase, such that WB dash will decrease, such that WB remains constant. As WB dash you said decreasing, that means what? As the width of the base is decreasing, what will happen is, you have here one current you are sending as emitter current here. This is emitter current, and this current is dividing as base current IB, and the remaining current is going to collector like this. So what you said is, this path whatever you have created, that width is decreasing, you said. How much width decreases, that much current will decrease. Therefore, if this area, if you increase more, you will get more current. If you decrease it, you will get less current. That means IB is affecting there, your IB current is getting decreased. As the operating width decreases, the base current also will get decreased. As the base current decreases, automatically collector current will increase. If IB current decreases, your output current IC will increase, because IE current is fixed. If I send a constant current here, you are decreasing this current, then the remaining current will increase. So finally what he want to tell is, the mechanism says that in active region concept, your current is saturated, we have given in the graph theoretically, but current is not constant in active region, current is increasing, you want to tell in the subject. That means the output characteristics, whatever we studied till now, is a theoretical study. But really if you want to study like a practical system analysis, I think the current is not constant, the current is increasing in electronics. The current is increasing there. So let us understand in a graph that how the current, you can show the current increase, that I'll show you. This is called the mechanism, how the early effect has explained the concept. This is called early effect. Thus, you are going in wrong way. Current will pass through depletion region only. Current is going from depletion region to the collector region. We cannot say that in depletion region current will not flow. What I am telling is, in this region there is no current flow. Only in that region I am telling. From the emitter when you are passing the current, it is going to the collector by crossing the depletion region. But this base current cannot flow in this region. It can flow in this region I am telling. The base current whatever you created, it has a current flow in only from JE junction to the boundary of the depletion region. That I am telling you. This current you cannot show here. Okay, that is immobile ions region for us. So the current flows will be between JE to this boundary level. That is called base current will flow. That I am telling you. Why IC increases due to less base width means as the base width decreases more and more. This here in next classes I'll tell you some terminologies. Now I cannot use the terminologies for electrical students. We call it as a recombination. The recombination will decrease there because the width decreases, recombination rate will decrease. Base current is called recombination current. If this current decreases, automatically the remaining current will increase. Because ultimately, if you have the fixed current here, this current decreases, the remaining current will increase. One current you are decreasing, therefore the other current will increase. That is the way you can understand the concept. Sumanta, please here, W dash, why it is increasing, how can you ask like that? Already I have given a good knowledge about diodes here. Statement bata raha hu na. Either I taught here, then I am teaching there. I am not directly going to the class like this. Electrical students है मेरे को मालूम है. उनके लिए इधर statement क्या लिखा? If output junction is reverse bias, the depletion region is wider. Means what? The depletion region will get increase in reverse bias. Here reverse bias voltage is VCE, my friend. As VCE increases, the width is increasing here. Means W dash I consider as a width of the depletion region that is increasing. So a statement लेकर a link बता रहा हूँ nicely. Then you should not confuse with that point. Okay? So please complete it. This is the story actually, which will be covered in device part actually. Electronic devices. Maybe at this point it is required for me to teach. That's why I'm teaching this point here. They're all device portion concepts. Vishal, I think now it is clear. I'm expecting why IC is increasing means as the base current decreases, IC current will increase. Because ultimately if we keep IE constant there, IE is equal to IB plus IC. When one current is decreasing, the other current has to increase. Okay, that is the meaning. So if IB decreases, IC will increase. If IB increases, IC will decrease. Opposite. So anyway, this is the story. What you have to learn, background knowledge for the early effect. as Mangal, IC current will flow definitely. The IC current will cross this depletion region. There is no trouble about that. Okay, the current compulsory has to pass through depletion region. But inside the depletion region, you cannot create the current, I'm telling you. Okay, from outside you can cross the depletion region and come current to the next side. But I'm telling you, inside the depletion region we have some immobile ions. Okay, we cannot create the current inside that. But you can send the current crossing the depletion region, I'm telling you. Okay. We can say immobile ions are in P side. Yes, ions are negative ions. Yes, Arpita, whenever you talk ions, please have this knowledge. This is a NP, P material means negative ions I have taken, for example, for it. Okay? So please complete it. Let us have a graph for this, no? Let us understand the graph. So you are telling that in active region, IC current will not be constant. It will increase, you are telling in the class, with this early effect. So it will increase in the concept. Note down nicely, this topic is very important for understanding. Yeah, Ayan, sorry, just for this idea, I have written for rough case. NPN or PNP, don't bother. Okay, if it's an NPN, I think IC current will go in this direction. So if you have that confusion, you can change it, no problem. It's only for study purpose I have written, roughly. If you particularly think about NPN, Ayan is telling the direction if you want to show, you can show like this. But finally, what is our meaning is important. Direction is not important here at this experiment. If it's an NPN, the direction will be like this only, but my meaning is, if this width decreases, IB should decrease, that you have to understand it. Because NPN or PNP, anything you can explain that. That's not an issue. So in the notes, if you want, without confusion, you can take NPN, I have taken example, so direction you can change. Okay, Ayan, I hope you understood it. Direction is not a matter here. So anyway, now let us see in the next slide about the graphical knowledge. So if you see the output characteristics, we have studied the graph like this. Theoretical graph and practical graph will come both at a time now. This is VCE and this is IC. Till now our graph knowledge is like this. This is our knowledge till now. This we have taken it as VCE saturation, which is equal to 0.2 volts. This is the way how we studied till now all the circuits in BJT. Correct? This subject who study like this graphs we call it as theoretical studies in the class. This concept we call it as theoretical studies. Okay? And if I ask you what is the current here? Theoretical current, IC. Suppose you ask me, can you tell me what is that IC current in active region? Then my formula will be IC is equal to IS into e power VB divided by VT, which is a diode current, which I studied in our classes. So I can define my collector current in active region as a diode current, which is coming from the input junction diode. So IC is equal to IS into e power VB divided by VT. But this current we call it as a theoretical current. This is called as a theoretical current. So that means you are a theoretical person till now. But if you want to think like a practical person, I think you should not think like this, he said. Early scientists said that if you are really a practical person in the experiment, I think it will come like this up to saturation point. Up to saturation, we are getting same line. But whenever you cross VC values more and more you are giving, reverse bias if you are increasing, I think your line is coming like this. So I think your current is increasing linearly history. Your current is increasing linearly. Your current is increasing linearly like this. So this is actually the deviation coming from theoretical to practical study in devices. So every time remember, there will be two issues now onwards in amplifier classes or current mirrors, wherever you go. One issue is theoretical issue, one issue is practical issue. Practically, anybody asks you, in your active region, the current remains constant or increases. You have to tell that it will increase, not constant. Okay? It will increase, not constant. Then what is this current? We'll take it as a practical current called as IC dash. There's a new current for it. Theoretical to practical current. How we define this current is IS into e power VB divided by VT. And he has written some extra parameter for practical current. What is that extra parameter is? 1 plus VC divided by VA. This is an extra term he created called early scientist. That means as you're increasing VC value, I think there's a linear expression so that the current will increase linearly, he said. But what is this extra term, VA? You kept some word there. Early has kept some word, VA. What the VA signifies here is, the scientist said that every transistor will have some deviation like this, practical. So why can't you draw this line? Why can't you extend to the second quadrant like this? Such slope, you extend it to the second quadrant. And just it will intersect somewhere in the second quadrant. Whatever the deviation will come for your BJT devices, definitely this deviation is for every device practical. You just write a slope line to the second quadrant, somewhere it will intersect. Somewhere it will intersect here. That voltage, he has given a name called VA with modulus. That means VC, I have given the name as VA in the second quadrant side. So at that voltage, what is the condition here is, at this voltage, automatically you can see your IC dash will become 0. That means your practical current will become 0 then. So that is a meaning called early voltage. This is a practical current. One is theoretical and one is practical. So whenever you reach VA, your current IC dash will become 0. Practically the current will become 0. Then what is this extra letter means in the class? Let us see the point. So this we call it as early voltage now onwards. This indication we call it as early voltage. Now we'll see two cases. Early voltage is better for which device at what time you can see. He said that if early voltage, who will say infinite, is good or bad? If anybody asks me, if early voltage is infinite, if early voltage is 0, which is a better transistor? If anybody asks me, according to my knowledge, this yellow line and the white line, if they match each other, the transistor is a good transistor. If suppose your yellow line is going far away to the theoretical result, your transistor is the worst transistor you design. That means we can tell the quality of the transistor by the slope. If the BJT have the slope very less in the lab, if you do an experiment on the device, then you can say it's a good transistor. If the slope comes more and more deviation in the lab, that means you are not designed a good transistor. That means the difference will tell you about the quality of the transistors in electronics. So the quality will decide by VA. If VA is infinite, what do you mean by that? According to this equation, what is the story? You can see. He's telling that when VA is infinite, your IC dash will become equal to IC. This is the first condition we are getting. IC dash and IC means theoretical current and practical current both are becoming same. You can see in the formula VA will keep infinite there. This current and this current are becoming same. So it's a good transistor we can say. But in the second case, who will say second one, VA is 0. The IC dash will become here infinite. IC dash will become infinite because VA will keep it 0 there. 1 by 0 will become infinite. Infinite into any value will become infinite. So this is infinite deviation is coming current for you. This is coming IC dash is equal to IC. So which is better for you in the class is this is a good BJT we can say. Good quality BJT it is. This is a good quality device. It's a good quality BJT. It's a bad quality. Like this quality you can explain for a device. Bad quality BJT. So that means that is the main importance about your VA in electronics. VA will tell you how much good quality transistors you have been manufactured. So in VLSI, we don't know which transistor is good or bad. That's why manufacturer has to give the name VA for every device. If VA comes more, you can say that it's a good device. VA comes less, you can say it's a bad device. So practically, sir, how much VA should be? You said infinite. That cannot happen. Theoretically, it is infinite. But practically, how much? Means for a good transistors, practically how much? Practical value of VA is equal to 1000 is a good for BJTs. So who said 1000? That's a good quality. Who said below 1000? Who said below 1000? Like 500, 200. That means your quality is getting decreasing there. So high quality if you want, VA should be high in the class. Okay, that's the meaning. So these are the things, are common things for us in electronics to learn in device part. Okay, they're all electronic device part concepts. So finally, electrical student also maybe understood certain view about this early effect of concept. VA means importance is this one. With that importance, what I can do is generally here in active region, what we are doing is our transistor BJT is working like a current source I have created in the class. It is working as a current source. Correct? Current mirrors, what we done is we have biased the transistor loads to work like a current sources. So it is working like a current source. But ideal current source, if you want, output resistance should be infinite. But in this case, how much output resistance we can find out? The slope of this resistance is nothing but 1 by R naught. So we can find out from quality, we can find out the output resistance of your current sources. So that is the talent we are getting by early voltages. Now let us find out a formula how to calculate the output resistance. Is the main job for today class. So with the help of early voltage, examiner will ask you, please calculate the output resistance for the slope. So calculation of R naught. Calculation of R naught. Okay? R naught. Calculation of R naught. What is R naught here is? It is nothing but output resistance of common emitter. C, common emitter. This R naught is nothing but output resistance of common emitter we are finding. Because we don't have ideal current source, we have practical current sources. When you have some slope, means your resistance cannot be infinite, cannot be zero. It will have some value. That value we can find out with this slope. So how to find out the slope is 1 by R naught. First we'll find out. From the graph, we'll find out slope. Slope is nothing but derivative of IC dash by derivative of VCE. You can solve it. Derivative of IC dash divided by derivative of VCE. Solve this answer. It is not more than your IS into e power VDE divided by VT into 1 by VA. You can see the derivation of this. You can see the derivation. Just this formula I have been derived with respect to VCE. When there is a VCE is derivative is 1, VA will become 1 by VA. So you can write this answer as 1 by R naught will be equal to, this answer is IC. Theoretical current, IC current is that value divided by VA. So this is called slope of your graph. So slope I found like this. Very simple formula it is IC by VA. It is not IC dash by VA. IC is called theoretical current, which is nothing but the operating current of your biasing circuits. They will use some biasing circuit. We are calculating IC currents in our classes. That current. Otherwise, if you have doubt, you can write this as ICQ, which will come from biasing knowledge. ICQ divided by VA will give the slope of that line. So we can easily find out the slope now onwards. 1 by R naught we can find. But if you want R naught, output resistance, then simple logic is, if you want to know what is R naught, then the formula will be very important formula. It is throughout the amplifier classes. So I'm writing a big formula, VA by your ICQ, theoretical current. So this is the very interesting formula. Today onwards you have to keep in practice. So this is the standard knowledge we have. So anybody can find out now onwards in any problem, amplifier questions, who will do early voltage, he can find out the R naught value in the problems. Okay, output resistance we can find out. Suppose in the exam he said, if VA is infinite, they'll tell you. So you have seen already this question somewhere in BJT class, correct? Somebody asked me, sir, VA is infinite is giving, nothing is there. Who will say VA is infinite? The meaning is your output resistance of your common emitter transistor will be equal to infinite is there. So it is infinite because R naught is directly proportional to early voltage. So you can treat this current source, whatever you are showing, as an ideal current source you can explain. When VA is infinite, the current source, BJT current source, I, becomes ideal current source. It will become an ideal current source because we don't have any resistance parallel to current source. So that is the meaning of your subject called ideal and practical thinking. So in the coming classes, practically also I'll explain, ideally also I'll explain. You should have a deviation between these two topics with this content. This content is practical equation, this content is theoretical equation. So this completes my total knowledge about the early effect analysis. Okay, so let us complete this part. So I covered the total issue. So it is easy for me to teach in MOSFET. MOSFET will not take much time now to complete it. It will be comfortable now. Because any transistor you take, MOSFET you take, or you may take BJT, this concept will happen called in current saturation, the current will increase. There we have channel effect, here we have base width effect. Both will have the same impact. One is having channel effect, one is having base width effect in the concept. Yeah, theoretical you can consider it as an ideal nature. Okay, theoretical and ideal will be same in the class. Practical is different. So be clear about this concept. Yes, Anupam Das, we can consider theoretical one as an ideal one in the class. So please cover up here the total board. Nicely write down all these important points. What is this? Shavanidas? Yeah. In these problems, eta, I consider it as 1. Okay? In all these problems, eta, which is ideality factor, default I'll take. If I don't write anything, means it's 1. Okay? In exams also, if they don't give eta values, default condition is at 1. It can change 1 to 2 any value. Examiner will give that. You don't worry about it. If they don't give anything, you just consider it as 1. In the class also, I'm not considered eta. Means I assume that eta is 1, which is ideality factor for us in diodes, which will come here somewhere, eta. Okay? I'm not considered eta means it is a default, we can take it as 1. So in the exam point of view, this total information is not important. This information is important. This formula we should not forget. Output resistance always be calculated with early voltage divided by operating current of your transistor. Okay? This formula is recursively used in the coming classes in amplifiers. So if you don't know early voltage, we cannot define the output resistance of a common emitter transistor. If you know the early voltage, we can define the common emitter output resistance. So with this, we have covered the main concept. That is what is the story of VA we completed. Just we will convert that knowledge to lambda in the class now. Okay? It will become easy for you, lambda knowledge. So please tell me if it is completed. We'll move to the next point. Okay. Please tell me if it is completed. We'll start the final issue now. That is our concept of lambda. That also I'll tell you. If that will stop this analysis, we'll go to the second topic. That's called current mirror techniques. I'll explain. So let us see the next slide. One more. Keep the subheading as lambda. Lambda story I'm teaching. In brackets you can write channel length, modulation, coefficient. Channel length, modulation, coefficient. I don't want to teach this all stories for you. Just straightforward effect, I'll show you the concept now. As this transistor, MOSFET is also telling same issue for you. Because of channel length effect, we see VDS we have here. We see how ID. Straightforward graphically I'm teaching the class. VDS, ID. Theoretically I studied in the class the graph like this. Every time you study theoretically like this, which is a VDS sat is equal to VGS minus VD. This is called theoretical graph, where the ID current is a theoretical current. We got the answer as in current saturation as Kn into VGS minus VD whole square. This is the way how we studied. Without taking that channel length effect. Just like without the base, channel length is also changing with respect to VDS, drain to source voltage. So whenever this effect comes, automatically your graph will vary compulsory like a practical situation. Up to here you will get the same story. That's why easy to understand the subject. Here also you get the same concept. Therefore, this early scientist what he said, the same thing I have done here also. Here, just I marked one point. So this is called theoretical to practical now. This becomes here ID dash is equal to Kn into VGS minus VT whole square into brackets 1 plus lambda times VDS he has written. So what is the difference between the bracket terms? Previous person has written 1 plus VC divided by VA. Now this person has written 1 plus lambda into VDS. So what is the difference I'm saying in the classes? So whatever the mark you said here is VA. This is called early voltage principle. We apply same concept. Okay, that's why VA will be the marking for it. But in this class, actually early effect has been predicted in the concept of BJT devices. But that is happening in MOSFET also actually. But in MOSFET, there is a mechanism called channel length is vary with respect to reverse bias voltage. Channel length is vary. Because of that, they are not denoted with VA. They have changed this letter to 1 by lambda in the concept. So in place of writing VAs, they write here 1 by lambdas. Lambda is nothing but channel length effect. If channel length effect is not neglected by you, lambda will be 0. If channel length you have taken effect, then lambda will not be 0. So that is a meaning called lambda, which is inverse to early voltage. Who said lambda is 0? That means channel length effect is neglected. Channel length effect is neglected, you are taken. Means you are not considering the effect. Who will not consider this channel length effect in the classroom? He will get like this. He will get a constant current, called saturation current. But who will consider it? Lambda is not equal to 0 if you give in the problems. That means channel length effect you are considering. Channel length effect is considered. Channel length effect is considered. So one person, if you want practically, this graph if you want, lambda will be not equal to 0 for him. So who will say lambda is equal to 0, this concept will happen. If lambda is not equal to 0, this concept will happen. One is theoretical, one is practical knowledge. This concept is a theoretical information. Theoretical. And this information is a practical information. One is a theoretical and one is a practical information. So this is the story here. When I know BJT complete knowledge, doing MOSFET is similar to the BJT class. So no need of extra stories. Channel length will be affected neglected. Here channel length we are considering the class. So these two equations will play key role in doing the problems. One is practical issue, one is a theoretical issue. Then sir, how you got this answer? How you got this answer? Lambda into VDS means very common sense point. 1 plus VC by VA is your previous formula. In place of VC, I have written here VDS. In place of VA, I have written 1 by lambda. Are you understanding? VA is in the denominator. I have written 1 by lambda. Then reverse answer is 1 plus lambda into VDS. Like this, we are studying the concepts. So what about R naught formula here is? Okay, output resistance if you want. Output resistance. The formula is similar to this concept, BJT class. You got R naught formula in BJT class is early voltage by ICQ, but here we write IDQ. In place of writing ICQ, we write as IDQ here. But early voltage we are not talking here, lambdas we are talking. So we just convert into lambda formulas. So the formula becomes here 1 by lambda times of IDQ will be the problem calculation. So the only difference here is in BJT classes I give VS, in your MOSFET classes I give lambdas. But lambda is reversed to the early voltages. So that is the reason if I don't want to consider the circuit as a practical design concept, I'll say lambda equal to 0 in the questions. Previously in workbook I think you have seen lambda equal to 0 means is explaining this graphical study. It's just normal theoretical study we are doing. If lambda not equal to 0 is said in future classes, you think that we have to develop this concept. 1 plus lambda into VDS we have to consider and we have to do the problems. At that time, R naught will be not 0, R naught will not be infinite, it will have some value or less mega ohms. R naught will come in mega ohms generally. Okay? Rahman, actually you are asking, when BC is reverse bias, then IC will be 0 you are telling, that is wrong thinking here. Generally in our transistor BJT, our formula is IC is equal to 2 currents, not 1 current. One is alpha times of IE, which is coming from emitter junction, which is crossing the depletion region and coming, plus one more current is IC naught. We have 2 currents, my friend. Okay? As a VCE, you are increasing means only this is current is saturated. Your reverse saturation current is saturated. But this current is not coming due to VCE, it is coming due to VB voltage. So always in your mind, remember, 2 currents will come at the output. One will come from the input, one will come from the output junction. So how can you say this current is 0 here? It is unbelievable to say it is 0. Rahman, I hope you recollected the knowledge. Whenever reverse bias voltage you applied, you are telling that IC current will become 0. Use the theoretical knowledge here. We have majority current plus minority current, which we studied in our previous basic classes. In testing part fundamentals, we have studied alpha E is the current come from the input emitter, and IC naught will come from the reverse bias voltage. So IC naught itself is not 0. It is a minimum current called microamps and nanoamps. So the current never be 0 here as reverse bias voltage if you apply. The current will come in milliamperes because the input current is in alpha E is in milliamps. Okay, so you cannot say like that. IC will become 0 is wrong thinking. WB is Sochanani. Okay, so this formula is the best formula for doing these problems. I think now the students have clarity. Okay, practical whenever I teach, I take this style of equations. Theoretical whenever I study, that 1 plus lambda VDS I try to leave in the problems. Okay, that is the story for today's class. The first module is completed. Next we have is current mirror techniques now. We'll finish off, only 2 topics are there, easily they will complete. That's not a big issue. One is simple current mirror I'll teach now. One is a Wilson with the knowledge of practical analysis today. I need this knowledge because I want to teach in practical situation now, the concept. There is some problems are coming for practical MOSFETs in the class that I teach in the concept. So let us start our main journey now. Till now I have spent time only for device part knowledge to understand what is early voltage and what is lambda. I'm expecting each and every student who has understood, who has seen this concept, I hope your mind is injected with these 2 parameters. One is lambda, one is VA. Okay? I'm expecting this to inject in your mind. In the next classes, don't keep doubt faces when I'm teaching VS and lambdas. Okay, number of times I cannot teach. One time I'll teach, try to keep in mind the 2 parameters. A lot of time I have taken to teach only these 2 points. Nearly I started my class around 11:30 I think. Now it is becoming close to 1. Nearly I think 1.5 hour approximately I taught only this topic. Okay, so you should never forget these 2 parameters. I have invested a good time to understand these 2 points. One is lambda and one is early voltage. With the help of lambda and with early voltage, we can find out the slope of these lines, which is nothing but output resistance of the transistors we can find out. Okay, so please complete it. We'll start our journey up to 1:30. We'll complete some issue. We'll take a break. The remaining issues will be completed after the break. At least current mirrors we can complete by 1:30. So please keep these 2 points in mind here. Never forget these 2 letters. Okay, it will play a very key role in our next advanced analog electronics. Advanced means if you go in studies like VLSIs, these terms are very common terms for us. Lambda, because in practical designs they never touch theoretical stories. They touch practical stories. Because in real world we want practical, not the theoretical stories. For easy purpose in the exam point of view, or to ask a question, they'll go for theoretical situations. But you should have a talent to understand practically how to do, theoretically how to do. Both you must have the knowledge. So let us start our journey. Second topic I'm entering. Topic number 2 I'm entering called as MOSFET current mirrors. MOSFET current mirror. MOSFET current mirrors. Keep it ready. MOSFET current mirror. I'll teach in 2 different ways the simple current mirror concept. Simple current mirror, first topic. Simple current mirror. This concept I teach in 2 cases now. Case 1. In case 1, I have taken lambda is equal to 0 and I'm studying the current mirror. Lambda equal to 0 means theoretically I'm studying my transistors. Okay, that means lambda equal to 0 means there is no channel length effect. Then I'm studying my class. What happens we'll see first. If lambda equal to 0 given in the exams, then how the analysis will be, try to see. My current mirror, you know how to design a current mirror. It's not a new issue which we done in BJT classes. Just only thing is I'll replace the devices only. MOSFETs I'm designing in place of BJT classes. This will take it as M1 transistor. This will take it as M2 transistor. This current will take it as I0, and this current will take it as your I reference. It's a simple current mirror. BJT you have seen already. So we'll take here W by L1 for the first transistor, and here we'll take W by L2 for the second transistor. So suppose W by Ls are different. The other terms are same, like mu and Cox are same. Only W by Ls I have shown you different. Now the person will ask you, can you find out the current transfer ratio for this current mirror? Okay, find out the current transfer ratio. Otherwise otherwise find out I naught in the problem. So how the logic we have to apply in case of MOSFET compared to BJT classes. Okay, the simple logic you have to understand. Can I say that whenever you contact like this, M1, now we studied in MOSFET classes, whenever there is a contact between drain to source, the transistor automatically will work in current saturation, correct? This transistor M1 is in current saturation, no need of testing. So we can write from that knowledge, I'm writing M1 is in current saturation, is in current saturation. What is the reason? Your VDS1 and VGS1 are same. Your VDS1 and VGS1 are same. So here you take this as VGS1, you can take from here to here. And this answer is VDS1, you can take from this point to this point. This VDS1. You take this answer as VGS2 from this point to this point. And this answer is VDS2, you can take from here to here. You write the different names like this. And we'll see whether they are equal or different. One by one we'll try to understand. So first is VDS1. This VDS1 and VGS1 are same from the board. And that is the reason I said it is in current saturation straightforward. M1 is in current saturation. Current saturation indirectly called active region. You are under active region. So whenever this answer is a VGS1 biased by VGS1, can I say this point also will be equal to VGS1? So what is I reference current here? In the board is, if you want to calculate I reference current in MOSFET, it is V minus VDS1 divided by R will give the I reference current. V minus VDS1 divided by R. But VDS1 and VGS1 both are same. So we can write this answer as V minus VGS1 divided by R. So this is my I reference current in the class. So just I understood how to calculate the I reference current. One time if you know the I reference current, next job is, previous in BJT class there are some base currents are going here. But the best point in MOSFET current mirror is, you can take straight forward, this as 0. You can take straight forward, that is 0. And this current will take this as your ID1 current. So you can see in MOSFETs I said they are very high input impedance devices. So there is no story of currents flowing here. But in BJT class we have that problem. That's why we have gone to modified current mirrors, base compensation techniques, all these things. In MOSFET we don't require. Automatically the current will be 0 because gate current never enter into the MOSFETs because of the oxide layer. That is the greatest advantage of MOSFET theory. So any number of loads you connect, the current will not go to the gate voltage. So the beautiness here is, as the gate current is 0 here, what happened is your ID1 current is becoming your I reference. That is the beautiness in this device analysis. You're exactly the first drain current of the transistor became I reference, which is very important for ideal current mirror. That's why MOSFETs will behave very close to ideal current mirrors compared to BJTs. So up to here, I think story is very common, issues are going on. So ID1, we can write it as I reference. The second point here is M2 transistor, whether it is in current saturation or not, how to decide. So M2 to keep in current saturation, M2 to keep in current saturation, what you have to do is, M2, we are not biased or anything. In the future, you will get some circuits here, but this has to bias it in such a manner. This voltage, whatever you will get in the sub-circuit it is, you will get some voltage that should be greater than VGS2, you have to make it. So your VDS2, we have to make greater than or equal to VGS2 minus VD. If you satisfy this condition, then M2 also will be in current saturation in the coming classes. Because this voltage depends on the top circuits. Whatever you are designing in future, in VLSI designs, you will have some circuits here. The circuits has to make in such a manner, whenever the drop comes here, VDS2, that should be more than VGS2 you have to maintain. Then automatically that also will be in current saturation. Okay? That is the story. Now the point is, these two voltages are in parallel. That's why we can write here a condition. Your VGS2, here VGS2, VGS2 and VGS1 is equal to VGS you can take. Both are parallel, so same voltage will be there. VGS2 and VGS1 will be equal to VGS. So can I have the current now? What is this current? If I want to find out what is the current equation is, if it is in current saturation, your I0 can be written as your Kn into VGS2 minus VT whole square. You can write like this. And what is ID1 here I not defined? It is Kn. Sorry, don't write Kn. You write the total formula, it's better. You write here total formula. It is half into nu n Cox W by L1 first transistor into VGS minus VT whole square. So as VGS1 and VGS2 are same, you can write both sides, same answer. Here VGS you can write VGS minus VT whole square. But here we'll get half into nu n Cox. Second transistor is W by L2. Here VGS minus VT whole square will come. So both the cases you are seeing two equations like this. Second transistor current saturation equation is like this. First transistor current saturation equation is like this. So from 1 and 2, this is 1 and this is 2. You have two equations. So if I want to write the current transfer ratio technique, if I take 2 by 1 ratio, what is the answer will come? You can see. If I take the ratio 1 by 2, sorry 2 by 1 I am taking. 2 by 1. If I make, what is the story here is, I0 by I reference will be equal to W by L2 divided by W by L1 is common. You can see if I divide these two terms, you are getting the answer like this. I0 by I reference if I divide, half is cancelled, nu and Cox up to here they are similar, but WL1, WL2 suppose in the exam they are given different, then you have to take into ratio, and VGS is same, VD is same, so they are cancelled. All these things are cancelled. So this ratio will be the formula for simple current mirror. So I0 will be equal to I reference into W by L2 by W by L1 is the formula for doing MOSFET questions. So finally I got the formula. It's a very simple formula. It is I reference into second transistor WL divided by first transistor WL is the formula. In sometimes exams WLs will be given same. At that time you can take I0 is equal to I reference. Sometimes they'll give different, and according to that you write the I reference into some value of ratio will give the I0. This is my style of studying current mirror techniques using MOSFET analysis. This is called case 1 or theoretical way of studying. Then practically if I study, what is the difference will come? That also I'll explain you. Take this as theoretical study. Theoretical study is completed. Keep a formula like this. Every question you can do it. MOSFET questions solutions are easier. Just you must know the relation, how to write the current transfer ratio. So up to here, please complete nicely. Simple current mirror, case 1 is completed. Let's study this without being on here. As a VGS1, VGS2 both are parallel. Okay, I have taken it as generalized word VGS. Okay, that is the reason I have taken VGS as a common word for both the values. That's why these are cancelled. VGS minus VT has been cancelled because of that. As I have taken WLs are different, that's why you are getting in the formula WL ratio there. In exams, they'll take different WLs, so practice this formula will be better for you. It is W by L2 by W by L1 into I reference. With that, easily you can solve these questions. I'll go somewhat in practical depth now. Let us see what is the trouble in practical situation. Ideally or theoretically, okay, there is no problem. I'm getting a good equation. I'm very happy for that. But practically, there is some trouble is coming for me. Practically, trouble is coming. Okay, let us go to the practical issue. Keep the heading case 2. Second issue is case 2. Keep the heading case 2. Case 2. Case 2 analysis. Case 2 analysis. Similarly, thus M2, you should not say like that. We are designing the circuit. We'll make the circuit in such a manner. We'll try to keep in current saturation. You cannot say that it will be failure. ये हमारी हाथ में होता है design. So we'll try to design the circuit in such a manner. This condition compulsory. I'll make you satisfied. Otherwise, we will not design it because we want current saturation. If it is not working in current saturation, there is no meaning of current mirror here. So we are interested to design in current mirror. So this is our issue. How to design? But everything we can do it ourselves. Only thing is a condition satisfied. Okay, to make a current mirror as a load for you. It will not satisfy is not the meaning. We can satisfy it. We have to satisfy it. Okay. Let us go for the case to study now. Second point. B point. Again, simple current mirror. Simple current mirror. Keep the heading. Simple current mirror. And you write here, lambda is not equal to 0. How to think the subject I'll show you. If lambda is not equal to 0, how I'll think the design again. This is your R. B. We have the MOSFET. Simple current mirror I'm taking. Same story. This is M1. This is M2. This current is I0. No current will flow to the gate. This current is I reference. This is VGS you can take. And this is also VGS because they are parallel. Same you can take. But here, I cannot take VDS1. Whatever you are taking here, I cannot take here VDS2. Same. That is the problem coming in the concept. If you observe clearly the board, VDS1 is equal to VGS1 that we understood in the class. But VDS2 is not equal to VGS in this concept. That means this answer will not be same in simple current mirror. Whatever you do, that two answers will not be same. So now, why sir VDS you are talking means you are talking about lambda not equal to 0. When lambda is not equal to 0, VDS will play the role now. Problem is coming with VDS. So the only story is now the equation changes like this. Your ID is equal to half into mu n into Cox. W by L will come into VGS minus VT whole square. This is the complete theoretical equation into 1 plus lambda into VDS. This is an extra job you are getting in the concept. This equation will be valid for current saturation. Current saturation. If the transistor is in current saturation, this equation is valid where lambda is not equal to 0 you are telling. Lambda is not equal to 0 you are telling. That means you have to follow this equation in the class where VDS here in the board if you see they are not equal. So now according to the board, observation is VDS1 is not equal to VDS2 in the board. Both are not equal. Okay, why they are not equal? This voltage is this voltage plus this voltage. They are getting 2 voltage. This drop plus this drop is VDS2. But here VDS1 is only this drop, so they are not balanced. So VDS1 and VDS2 both are not same. If they are not same, what is the problem will come here is first current is I reference current you can write, which is your current equation half into mu n Cox W by L1 you can take into VGS minus VT whole square into 1 plus lambda VDS1 we have to take. 1 plus lambda VDS1 I have taken in the first case. So second case we take this as equation 1. Second case I0 is equal to half into mu n Cox W by L2 will take into VGS minus VT whole square into 1 plus lambda into VDS2 we have to take. So I think we have two different VDS values with lambda effect. So you take this as equation 2. So if I ask you what is current transfer ratio, 2 by 1 if I do it again, it is I reference I0 by I reference. If I take it, current transfer ratio you can see, what is the answer? This total part, this part is cancelled. So you will get W by L2 by W by L1. You are getting like previous case. But not only that, here this quantity is not cancelled. 1 plus lambda into VDS2 by 1 plus lambda into VDS1. So have you seen the story now? Your current transfer ratio, whatever you got, is not only coming by W by LCR, you are getting by lambda effect also in the class. Lambda effect is also coming. So that means this answer is mismatch with I0 by I reference is equal to W by L2 by W by L1 in the class, which is a theoretical formula. This is theoretical, this is practical. So the practical one is not matching with theoretical one. So That is the main drawback about simple current mirrors. Whenever you take simple current mirrors, there is an imbalance of your equations. Actually, we are expecting this equation we want in current mirrors. Okay, but you are getting some extra quantities called 1 plus lambdas with VDS1, VDS2. If I want to resolve this problem, we have only one solution in the class is this voltage and this voltage, you have to make it balance. Whatever you modify the circuit current mirror, VDS1, VDS2 will get balanced it, then automatically this formula will fall under this category. So that is the reason why we are trying to study a new topic called Wilson current mirror. The Wilson, what he done is, he has balanced the current mirror in such a manner, VDS1, VDS2 he made equal, such that you can enjoy this equation when lambda effect is also there. So if you have lambda also, we can enjoy that equation in the class. That concept is called Wilson current mirror. How we made that VDS1 is equal to VDS2 is a story. Okay, that is the story. That is the last topic. With that we can stop this analysis. So today I think current mirrors are completed nicely. This is the only simple way of understanding current mirrors. Only BJT will take more time. Okay, MOSFET will be very easy and understandable. So only one topic is remaining. That's called Wilson technique. Wilson has to rectify this problem called as practical lambda technique. If you have lambda given in the exam also, this effect should cancel. That cancellation how to do with a new modified design called Wilson technique. That I'll explain you. With that we can close the story of concept called current mirrors. So you can see how much time it has taken. Teaching the background knowledge has taken 2 hours time for me. To teach the main topic, current mirrors, it has taken only 45 minutes or 1 hour max. It is not taking much time. That's why background will take more time in my class. When I attack the concept, it takes very less time to understand the analysis. So I hope you are enjoying this point from the previous background knowledge. Yes, Anupam Das, both the circuits have same relations. Only thing is, this lambda is differing the result of your theoretical calculations. The lambda story should be cancelled in the concept. We want in practical also. Sir, VDS1 is equal to VDS2. How it is 1? Could not follow. With this Sahu, I think here, in this case, VDS1, VDS2 are not same here. This relation why you are getting is, your VDS1 is not equal to VDS2. We got a mismatch, that only I am telling. This is theoretical formula that came in previous topic. A formula हम theoretical में किया, a practical में वो mismatch पर. So they should be equal. Practical or theoretical, you must get the same answer. Yes, mismatch is due to channel length modulation effect. Yeah, channel length modulation effect में problem नहीं आ रहे. Lambda is same. We have channel length effect came same for both the transistors I have taken. But problem is coming with your VDS design. So VDS you have to balance. Problem is not with your lambda. Problem is with your VDS design. Yeah, correct. Roy, what you said is correct. VDS1 and VDS2 are not same due to lambda. Lambda otherwise we got VDS1, VDS2. Let us understand how this Wilson has corrected this design. How he made VDS1 and VDS2, how he made same. That is a final trick. Okay? The technique we will understand. The concept is ready with the analysis. So that happily after the break we can start doing last topic called inverters. Okay? That is from 2:30 onwards we'll start analyzing the inverter techniques. Inverters also will take hardly 1 hour I think maximum. After that we'll continue with the workbook problems. Okay? That is the next job we are going to complete. I'm covering each and everything in the analog. Please try to understand and get the subject in a good manner. Okay? Each and every step we are covering. So this subject should look very easy after my completion of analog course. When you're sitting in the first day, okay, you are having so much of tension. That's how you teach the subject. Now maybe you're getting the confidence how I'm teaching the class. Okay? Starting में कोई भी को confusion होता है. कैसे सर teach करते हैं? How he is going to adapt the subject. Now you'll understand how the sir approaches the subject to make it more easy for the students. Yes, sir, Rahman, in previous case also VDS1, VDS2 are not same. But we don't have VDS1, VDS2 because their lambda is 0 here. हमको lambda 0 मिल गया. So VDS1, VDS2 different होने के बाद भी हमको WL1 by WL2 we enjoy it. But here we are not enjoying it. Okay, Rahman? So let us complete the final task. Keep the heading. Keep the heading Wilson current mirror. Second topic is Wilson current mirror. You can take B point it is. This is the B point. Wilson current mirror. Wilson current mirror. The main purpose of using Wilson current mirror is your VDS1 should be equal to VDS2. The target here is by Wilson model, VDS1, VDS2 same करना आपको. That's called Wilson concept. How we made this VDS1, VDS2 same. See the trick now? Design. The circuit how we design. You can see. This is your suppose reference current I have taken directly. This is I reference. This is your V. Next he has taken here one MOSFET. Next one more MOSFET. Two MOSFETs he has taken. Here one MOSFET. Here one MOSFET. Like this he has taken the MOSFETs. So you can see this is M1 I'll take. This is M2. Here we have current mirror. I kept current mirror like this. And here also I kept one current mirror like this. This is your M3. This is your M4. So actually the load is this one. This load is only M3 is the load. M3 is the load, active load. Where you want the current here as I0. You want the current I0. We have used some current mirrors here to balance the concept. Now the point is, whatever the voltage here we have at M1, we'll take this as VDS1 voltage from here. And whatever the voltage we have here, we'll take it as VDS2. Like this we'll take VDS1 and VDS2 in the concept. I want to make these two are equal in the concept. I want to make these two voltages are equal. That is the target. You consider this is your load, this is a feedback. In BJT class also we have taken this as a feedback. To adjust something, I kept one more MOSFET here. Okay, previous class, in BJT class we kept short there, but in Wilson we can have a modified version called one more transistor there. Let us target now, this answer, that answer, how I make it equal is important now. First point, current ratio is very good here in MOSFETs. You can see the current ratio, whatever the reference current is going here, it cannot go this side. You cannot get here, no current, no current. Okay, if there is no current here and here, the same reference current will go here, I reference. Will come same current. The same current, whatever you are seeing, the same current will come down. So you have same I reference here. That means for M1, you can take I reference as your first current, and this current can go directly like this, I naught, and this current will go as I naught. So you can have M2 as I naught current. Here M1, we have VGS is same here. VGS, I'm taking same. And the same VGS we'll try to develop here also. So here one VGS is there. Here one VGS, this is VGS. And this VGS is parallel to this voltage, so this also becomes VGS only from here to here. So carefully see this drop techniques. This is VGS, this is also VGS. This is one VGS, we have gate to source. This total voltage will be same as this total voltage because here short is there, 0. 0 plus VGS is VGS, so these two are parallel to VGS points. So now the point is, what is the answer for VDS2 is straightforward, it is VGS. This answer and this answer is same, VDS2 becomes VGS. Now the target is VDS1, how to solve? This is VGS and this is VGS, we have VGS plus VGS, this point will become 2 times of VGS in the class. It will become 2 VGS in the class, okay? This is 1 VGS and this is 1 VGS will become 2 VGS in the concept. This 2 VGS will come to this point. So here you will see 2 VGS here. This is 2 VGS, clear? Yeah. This is VGS plus VGS is 2 VGS, here also 2 VGS. As you short it here, this drop and this drop is same. This drop should come here. So it will become VGS from this point to this point. Gate to source voltage should be equal to drain to source voltage. Now finally, if I ask you what is VDS1 here in the problem, here VDS1, if I want to solve, you can write it as VDS1 is nothing but this voltage if you want. First of all, 2 VGS you will write. We write it like this. If you want VDS1, you start here. It is 2 VGS is equal to VGS plus VDS1. You can write a KVL there. You can write a KVL here. 2 VGS is equal to VGS plus VDS1. Then what is VDS1 here is? It is 2 VGS minus of VGS. So answer is VGS. Can you see the trick now? Wilson trick is this one. So finally, he brought VDS1 is also VGS we got. VDS2 is also we got as VGS. Therefore, your VDS1 is equal to VDS2. Finally, he adjusted the circuit in such a manner, VDS1 and VDS2 will be same. But to do design for this, we need 4 MOSFETs. One is load MOSFET, remaining 3 MOSFETs extra we need to balance this concept. It's one of the beautiful technique he applied to make your formula I naught by I reference technique is equal to W by L2 by W by L1 into 1 plus lambda times VDS2 by 1 plus lambda times VDS1. Can you see that this factor has been cancelled? Because of VDS1 and VDS2 are same, both are cancelled. Therefore, finally, this is the formula. So this is the way how this Wilson has given some prominent design for us to balance these 2 side voltages. Okay, this is a story about your Wilson technique. Yes, all MOSFETs are identical you can take in this concept. Because in current mirrors generally default the identical transistors we take. Okay. Anyway, the main job of Wilson what he done is the VDS1, VDS2 has balanced such that you may have lambda effect also. The theoretical formula we can have the analysis in current mirrors. So with this friends, we have been covered nicely. Within a short time we covered the current mirror techniques. With this we'll stop this. Remaining job after 2:30 we'll start the job on inverter techniques. Okay. Let us stop here the video. So who is writing? Write down. Streaming will be like this. Recording I'm stopping, but streaming will be like that. After this you can take the break. The break time we can start at 2:30. We'll start the class. Okay. Around 2:30 because it is now 1:30. 1 hour we'll take the break. 2:30 we'll start the class. Okay. 2:30 1 hour you can take the break. We have VGS, that's clear. This VGS is there. A VGS square करते हैं 2 VGS is coming. This 2 VGS from here to here is 2 VGS that will come here. 2 VGS. And this total parallel voltage will be same as this parallel voltage, so VGS will come. Because of the short, VGS is equal to VDS I have written. Then this minus this if you do, you'll get VDS1. Just एक बार observe करो. Drops कैसे मैं subtract किया. One time if you see, you'll get it. Again Divya Das is saying 240. 240 time में क्या है समझ में नहीं आ रहा मेरे को. Every time 240 बोल रहे. चलो. 10 minutes bonus you want every time. No problem. I'll start at 240. If you are happy with 240, we'll start at 240.